How's life? Good? You're not a scientist?
No, you guys said they're good because you called it science.
Oh, good. Good. All right. So, a great lecture for you again today. A delicious one. What have we done so far, folks? We have seen a whole bunch of abstract notions and trying to understand what it all means. So let me summarize very quickly. Okay, so our goal is to develop some sort of framework that can describe the electron in the atom as a wave. And that framework is different from the framework that we have been using to describe other particles like tennis balls or silver bullets. Okay? And this framework has two main ingredients. One of them is the actual wave function, okay, which has some funny properties. And the second important part was the operator. Operators correspond to physical observables like energy, momentum, position, and things like that. Okay? We've already seen that we operate with the operator onto a wave function, we get some information about the observable that corresponds to that observable. And in order to do that well, we have to compute the so-called expectation value. Okay, so that's something we have touched on so far. You've also seen that if you take the modulus square of the wave function, you get some information about the probability density or the whereabouts of the electron in a probabilistic way. Okay, so that's something that we have to keep in mind. And we saw last time that these wave functions can be very funny. Okay, they can be composed of so-called eigenfunctions or a sum of eigenfunctions, and in both cases we get different kinds of results. Okay, so today what I'd like to do is to tell you something about how do we get to such a wave function. What defines a wave function? What is a good wave function? What is a bad one? All right, so we have to know that because we'd like to have proper wave functions that describe our electron in the atom. So the main thing by which we define the wave function is a beautiful equation that we would call the Schrödinger equation. Okay? So the Schrödinger equation, and I'll show it to you in 2 seconds, helps us determine what constitutes a good wave function. Okay, so what does that thing look like? It looks like this. Look at that. Do you think it's pretty or not? It's very pretty, folks. It's very pretty. Okay, so what does it say? Let me just walk you through. You see the wave function is in there, right? That's the psi. So the psi is in there. It basically is a differential equation, as you can see. It basically says I'm taking the first order derivative of the wave function with respect to time. And that should correspond to the wave function again, but operated on by this h with a little hat that is called the Hamiltonian. That is the energy operator. Okay? So this equation links the wave function to the operator for energy, the Hamiltonian. That's the h. So if I'm able to solve this equation, and I'm getting from this what this psi looks like, then I have a good psi. Okay? You may ask, why is that so? That answer is a little bit more complicated. We will not dive into it. We will just assume that it is so. Okay, so this is called the time-dependent Schrödinger equation. Why is it called Schrödinger equation? Because a guy called Erwin Schrödinger made it up. Okay, and this equation works really well, and that's why we are still dealing with it. It also says time-dependent because time is explicitly in there. You see that? d dt, it says. That means it depends on time. Okay, so what can we do with this? We have to solve this. How? Well, let's try something. let's first look at the Hamiltonian. What does the Hamiltonian look like? We have seen it before. Maybe you don't remember, but it had two parts. One is the kinetic energy operator, and for now, it will just operate in one dimension, x. And in that case, it looks like this. A prefactor, which is minus h bar squared over 2m, and then the second order derivative with respect to position, x. There's another part, which is, of course, the potential energy operator, which can be all kinds of things, depending on the situation. Okay, we will specify that based on the case that we're looking at. What is the potential energy in a particular environment? It depends on the environment. So we can't say for sure what it looks like in general. Okay. Now, if I'm now looking at this Hamiltonian here, there is no t in there. There's no time. Okay? So if I look now at the Schrödinger equation, it says, well, the time dependence is actually on the left, because that's a first order derivative with respect to time, and there's no such thing on the right hand side of the equation. Okay, so what I'm going to do now, I'm going to say, if that's the case, then maybe I can separate the time dependence from the spatial dependence. So what I'm going to do is, I'm going to say this big psi is a psi that depends on x, and then some sort of function, which I give a name, theta. You can call it something else. This theta has no particular reason why it's called theta, but I'm just saying that's theta that only depends on t. Okay? And the product of these two things is the solution of this equation. And it actually is, because the first order equation with respect to time has a very nice solution. Okay? And that solution is basically this. It's an exponential function. It's an exponential function. So the time dependence of this equation looks like that. It looks like e to the power minus I e, where e is energy, the eigenvalue for energy, and then t is time over h bar. That is the shape of the wave function in time. Okay, you may not believe that, so I'm going to prove to you that that's the case. I'm going to just plug in that solution into this equation. Okay, so there we go. I'm going to take this general form. The general form is a product of psi x theta t. I'm going to put that form into that equation. I have to take the first order derivative with respect to time of this function. Okay? So that's what I'm going to do. I'm going to plug in this form psi x theta t and take the first order derivative with respect to t. Now, only this theta guy depends on time. The psi x only has x, has no t. So the derivative only acts on this theta t, and it has this form. Okay, so that's what I'm writing here. There you go. The first order derivative of this exponential function. That's what I have to do. You see that? That's all I did. I just take the first order derivative. I'm going to take the first order derivative of this function theta. And if I do that, I get, of course, the function theta again, because taking the derivative of an exponential function gives you again the exponential function, which is the theta. And then, of course, a little prefactor because of the derivative taking, and that's this guy between parentheses. Okay, so what I do now is I'm going to clean up this expression a little bit. Okay, I see there's I here, and there's also an I there. I times I is -1. There's another negative sign there. That cancels out. Okay, so when I clean up that expression, I get this. It's basically E, which is energy, times the spatial part of the wave function, psi x, times the temporal part of the wave function, theta t. What happened to the h bar? It canceled out. You see that? Because on one side there's h bar, and then a little bit further on it's 1 over h bar, and so they cancel out. So, beautiful expression that comes out. right? So that's good. So taking the first order derivative to the with respect to t of the wave function gives me the wave function again times E, times the energy. All right? Pretty good. Now, the right-hand side of the equation all the way on the top says if taking the first order derivative with respect to time must give me the Hamiltonian times the wave function. So the outcome here must be equal to the Hamiltonian times the wave function. This is again the wave function, right? Psi x and then theta t. That's the wave function. Which means that these last two lines are equal to one another. That's kind of interesting. So if I look at that carefully, I see on both sides there's a t here that can cross out. I cannot cross out this guy because the Hamiltonian is acting on it. I cannot divide that out. But I can certainly divide out the theta t. And therefore, I can make this statement. If this guy operates on the spatial part of the wave function, I should be getting the energy and the spatial part of the wave function again. This is nothing but an ordinary eigenvalue equation. It simply states that if the energy operator operates on its eigenfunction, it produces the eigenvalue, which is the energy, times the function again. This equation is the central eigenvalue equation in quantum mechanics, and it's called the time-independent Schrödinger equation for very good reasons, because the time dependence we have basically divided out. You see that? We only deal now with the spatial part. So this is the time-independent Schrödinger equation, and in quantum mechanics, that is the key equation that helps us find the shape of the wave function. We have to solve this equation. Okay? Sometimes it's very easy to solve, sometimes it's a pain in your behind. Also in my behind, by the way. So, let me write that down more generally. Again, the wave function, generally speaking, has this particular form. It is something that depends on space, psi x, and then times a function, which is a complex exponential function, which has in it time and also energy. Let's look at that a little bit more carefully. This is a general solution of the Schrödinger equation. All right? That whole thing is a general solution, has that general shape. So let's look at this complex exponent again. What is that? Well, as you probably know, you can write a complex exponential in this way, namely a cosine of the argument plus I sine of the argument, right? You've seen that before, I hope. And so in this particular case, it looks like that. So let's look only at the cosine. Let's forget about the imaginary part for now. And we see that the function, as a function of time, is basically, as t is progressing in time, basically you generate a wiggly function, an oscillating function. So this complex exponent is something that wiggles periodically as a function of time. So let's say I have a spatial part of the wave function, psi x, something like that. This is very similar to what we looked at last lecture. Okay, so let's say I have a space, 0 to L. Let's say this is my size of my atom. The atom is L wide. Okay? And my electron is situated between the point 0 and point L because it's somewhere in the atom. Okay, so and it has this shape. It has one maximum and it comes back to 0. From 0, max, 0. That's what it looks like. That's one particular shape. Let's say that that is a valid solution for psi x. What does it mean now? The total solution means that this psi x is wiggling as a function of time. Okay? So let's say half a time cycle later, it looks like this. And then half a time cycle later, this goes up to plus again. So basically it oscillates as a function of time. And the amplitude basically changes from plus to minus as a function of time. That's what the function says. It's a wiggly function as a function of time. Okay, but if I now ask myself, what is the probability density of an electron that is described by that wave function? What does it look like? So I take the modulus squared, as we did last time, and we see it basically is the same shape almost. Has still a maximum here. It kind of like tails off nicely now at the edges because of the taking the quadratic form of it, and you get this very nice probability distribution. In this case, you're most likely to find a particle at the middle of the box, the middle of the atom. But how does this thing change as a function of time? How does the actual probability of the electron change as a function of time? Does it change or does it stay the same? So let's look at that. What I'm going to do now is I'm going to take the entire wave function. I'm going to take the modulus square of it. So I'm going to take the very first equation on this slide, at the top. I'm going to take the modulus square of that. Now what happens if you take the modulus square of a complex exponent? What is that? That's 1. Okay, the modulus square of a complex exponent equals 1. So when I do this operation, I basically just get the the modulus square of the spatial part of the wave function. Okay, so the probability density in this expression does not depend on time. You see that? So if your wave function has this particular general form, I can say for sure that the probability density of my electron is not changing as a function of time. You're always sure to find it in the middle with the highest probability and the lowest probability at the edges. That's what it says, no matter what time. The actual wave function fluctuates, the amplitude of the wave function fluctuates, but its probability density doesn't. It stays put. Okay? So the probability density is time independent in this general form of the wave function. Okay, now on Wednesday we looked at a wave function that is now slightly different, namely it has a form of this kind, where it's not just one eigenfunction, but actually a sum of 2 with weighing factors. Okay? Why do I bring that up again? Because this is an interesting case. If I now ask myself, what is the probability density as a function of time for wave functions of this kind? Okay? Wave functions of this kind have several ingredients. In this particular case, a psi1 and a psi2, both are eigenfunctions, but they have their own eigenvalues. Okay? And the total wave function is basically a combination of the two. The total wave function itself is not necessarily an eigenfunction of the Hamiltonian. It is a sum of eigenfunctions of the Hamiltonian. And in that case, if I write out the entire thing, okay, you see that the oscillating term here and the oscillating term here are different because they have different energies in them, in the argument. They're not the same. So I cannot really divide out. I cannot divide out or just take out this wiggly term for both at the same time because the wiggly term is different for each. So if I take the probability density distribution of this guy, that's not the same as saying that I'm doing this. Because if I take the modulus square of this entire thing, the time terms don't cancel out or don't divide out. They are actually introducing combination terms that stay. So therefore, this is not generally true. You see, there's no time dependence in this statement here. This is not time independent in general. Okay? Conclusion here is the probability density of a wave function that's a combination of eigenfunctions of the Hamiltonian, not just one, but a whole series of them, that is not a wave function that has a probability density that is so-called stationary, that doesn't move as a function of time. There's actually evolution in this system. This system changes over time. Sometimes the electron is here, sometimes the electron is there. Okay, so if the electron is described
by an eigenfunction of the Hamiltonian, it stays put, it's so-called stationary. It's the same at all times. But if it is not, if it is a combination of eigenfunctions of the Hamiltonian, then there's actually motion in my system. All right? These are two very important cases in quantum mechanics. All right. So I'm going to now list two conditions by which the wave function must abide. Okay? The first one by which it must abide is this statement, that the modulus square of the wave function corresponds to a probability density. If I multiply it by a small volume element, I get a probability. A probability is an actual number. The maximum is 100%. The lowest number is 0. It must be something. It must be a finite number. That means that if I integrate my wave function, modulus squared, over the entirety of space, I must get a finite number out. That's one condition. The other condition is that the Schrödinger equation here, the eigenvalue equation, must have a solution. Okay? So this also restricts the shapes that the wave function can have, because a solution of this kind must be found. So let's examine now what are good wave functions and what are bad wave functions, just based on these two statements. That's the Hamiltonian again, same shape. I'm going to use that to make two statements in 2 seconds. But first, I like to look at this particular shape. Let's say I have a wave function, its spatial shape now, that's the only thing I'm interested in, looks something like that. I can say that this is not a valid shape of the wave function. Why not? Because this doesn't correspond to a wave function that has an actual probability density. An actually probability density, that makes sense. Okay? Because it's not single value. You cannot have a location in space where there is several types of possibilities. That makes no sense. If you are in space, there's a certain chance of finding you there. There's not like 3 different chances of finding you there. Therefore, the wave function must be so-called single value. It must have a single value as a function of space, not multiple values. The other situation is something like this. Maybe you've seen functions in mathematics where you have kind of like a singular point, right? Let's say, think about the hyperbolic function. Basically, it goes down to this side, comes up to that side, and basically, it's not defined at the actual pole. This is a similar function. It basically goes up, but it never really meets these 2 lines. Therefore, this is a singular point. This dotted line indicates a singular point. These functions are mathematically perfectly fine. But physically, they cannot represent a wave function because at this pole point, the chance of finding it there is not defined. It's not 0, okay? It's not less, it's not finite, it's infinite. You cannot have an infinite possibility of finding something somewhere. That's impossible. Therefore, functions of this kind are not good. They cannot be finite. Here's another scenario. What if the wave function looks something like this? So it comes up here, some kind of wiggly shape, and then suddenly whoop, pops down and it continues there. This is not good either, for various reasons. This probability is not well defined in this position, okay? And secondly, the Hamiltonian, as you see up there, has a second order derivative in it. The second order derivative must exist for every point in space. Here, it doesn't exist at point x. There is no second order derivative. There's no unique second order derivative in this function. Therefore, this shape is not okay. The function must be continuous. Okay, lastly then, this function certainly is continuous. It's also single valued, and it doesn't go to infinity anywhere. However, this is also not allowed because the second order derivative is ill-defined in this place. There's no second order derivative here. There's no continuous curvature of this wave function. Therefore, d squared dx squared doesn't exist, and therefore it's not a good solution of the wave function. The slope must be continuous. Okay, so those are all general statements I can make about what this wave function should look like. Okay, let's now look at the simplest form of the Schrödinger equation. Here it is again. This is the Schrödinger equation. Okay, remember, the Hamiltonian looks like this. I'm going to say now that the potential energy operator is zippo, 0. Okay, it's not there. So I only see this part of the Hamiltonian, which is taking the second order derivative with respect to x. Okay, so what I'm getting then is this part, that's the left-hand side of the Schrödinger equation. It basically says h bar squared over 2 minus, and then taking the second order derivative with respect to x of the wave function, and that must equal a constant times the wave function. So this is the full Schrödinger equation for a particle in one dimension, where there is no potential energy function of any kind along x. It's 0 everywhere. Question is, can I solve this problem? Basically, I'm asking, can you find a solution to a second order homogeneous differential equation? And the answer is, yes, you can. This is a relatively standard case in mathematics. And in order to clean up this equation a little bit, I'm going to divide out the constant on the left-hand side and put it on the right-hand side. Okay? So what I'm going to do is, I'm going to write it in this way. It's the same equation. I just divided out the constant on the left-hand side. You see that? Nothing magical here. Okay, so this is a pretty clean differential equation, but I'm going to make it a little bit more simple for myself, because what I see here on this side, there's now a whole bunch of constants. They're all constants. And I'm going to say, it looks ugly. I'm going to just, all these constants together are just one constant. So I'm going to call that k. Right? So I'm going to say that on the right-hand side, I simply have k squared times psi of x, where k squared is defined as the product of all these constants. Because it's a square, k looks like this. It's the square root of 2me over h bar squared. You see that? That comes from the constants right there, on the right-hand side of the equation. Okay, so what I'm left with now is a pretty simple looking second order homogeneous differential equation. Looks like this. It's not homogeneous actually, there's a source term in there. But the answer of that, or the solution of that equation, it's the same equation, is this. Alright? A constant times this complex exponent. That is a solution of that equation. Is that the only way? Actually, this is also a solution. Right? If there's a negative sign in front of the I, that thing also gives you a valid solution of this equation. Take the second order derivative with respect to x, and then you'll get negative x squared times the function again in each of these cases. So both are valid solutions of the Schrödinger equation in this particular case. Okay, so I'm going to write the general solution in this way. I'm going to say this is the most general way I can write the solution. It's something that has a complex exponent in it. And these a and b are just the weighting factors of each of those solutions. This is a general form. But I'm going to study this now to see what it means. Okay? Okay, so let's see what it means. Let's only take the first solution, a times this complex exponent. what does the solution actually mean? Well, the complex exponent, like we just concluded, is a Wigly function. Now, as a function of x. So what I'm getting is something that changes periodically as a function of, that's a wave in space. It's a wave in space. Okay, so the answer to this problem, this one-dimensional problem, no potential barriers anywhere in space, is a wave. One periodic wave. That's why it's called the wave equation. Okay. It says now between parentheses, let's assume that this A is defined in such a way that the wave function is normalized. Okay? Let's assume that. And now I'm going to compute what is the momentum of this electron that is described by the wave. So the electron is now described by a wave. And I'm going to ask myself, what is the momentum that this electron has if it has this wave function shape? All right, so I can do that. I can calculate the expectation value of the momentum operator, and it looks like this for normalized wave functions. We have seen this before now. Basically, it's the momentum operator, P with a hat, sandwiched between the wave function on either end. There's an asterisk there, that's important, because the complex conjugate of this function here is not the same as the function itself, because there's going to be a negative sign now, right? When I take the complex conjugate. Okay, let's compute this. It's not so hard, really. It looks weird, but honestly, if you do it a few times, it's not really that hard. Because the only thing I really have to do is to plop in here the shape, the form of the momentum operator, which is right here, and it says take the derivative of this function, and then integrate. Taking the first order derivative of a complex exponent is the function again times the prefactor, where the prefactor is ix. Not ix, ik. Okay, so what I'm getting is this. Hopefully you see that. What I'm getting is, after I do the first order derivative, I generate the function again times ik. Okay, because taking the first order derivative of the complex exponential generates just the prefactor times the function again. So that's what I'm getting. And because I said that the wave function is normalized, this whole integral is what? It's uno, folks. Meaning that I get this. H bar k. Why h bar k? Because this I canceling out, this whole thing is 1. K times h bar is the answer. The momentum of this electron is k times h bar. All right, how can I conceptualize that? Well, if the wave function describes an electron, and I can conclude that the wave function is a wave, and that wave has the property of the electron having a momentum that has a value k times h bar. Okay? That's the value of the momentum. So I could have taken the second solution form, that's this guy with a b in front and a negative sign and a complex exponent, and do the same computation, basically asking myself, what is the momentum of the electron if it would only be described by this? There, I see it in a second. So I do this calculation, same fashion. What do you think you get? You get the same answer, but now with a negative sign. Basically, it says the same value, opposite sign, basically it means you have momentum along negative x or positive x. That's what it means. Yes, you had a question.
Yeah, so on the previous slide, you mentioned that it said that psi A is an eigenfunction of the momentum operator.
Yes.
How did you determine that? Was that like a given or something?
No, I determined that by simply taking the first order derivative of the function, and what I get is the function again times a prefactor, which means a constant times a function again, it is an eigenfunction. Okay, so this is x. My dot symbolizes my electron. My electron is actually a wave. It's not a point in space, but it actually is a wave now, because that's a representation. And you raise your hand. Are you just scratching your head? Okay, good. And I have two shapes of the wave function. One is basically a wave traveling with momentum one way, and the other travels with momentum opposite sign the other way. Okay? So that's basically what it looks like. So, if I would make this A and B prefactor the same, then it looks like this, right? Then I can take this prefactor out, and what I'm getting is the sum of a complex exponent with a plus sign and a negative sign. Actually, that function is 2 times A times cosine x, cosine k of x. K times x, sorry. Okay, you can see that because whatever is between parentheses is more or less the definition of a cosine. The cosine is defined as half times whatever is in there. So I get 2 times A times cosine kx. This is just a cosine function. Okay, so that's what I use, the definition of the cosine in terms of the complex exponential function. So if I take the modulus square, I get the probability distribution of the electron, and I get basically a cosine function with a square in it. So if I now draw that, I just get this. This is the cosine squared. It's a function of space. What does it tell me? It tells me this. There are locations in space where you get no probability. The electron is never here. It's pretty high probability right there. Not here. Very high here. Not here. And so forth. So there's locations in space where the electron is simply not to be found, and other regions in space where it's very likely to be found. This is a so-called standing wave. This is a standing wave. It doesn't change as a function of time, and basically says there are regions in space where the electron is very likely to be found, and regions where you will never find it. What is the momentum of this wave function? It's 0. Because it's equal parts going this way, and that is the definition of a standing wave. It doesn't travel. This and this in equal terms, that's why I said A is equal to B, means the overall momentum is 0, and that is the definition of a standing wave. The standing wave has no momentum. The standing wave concept is important because, a little reveal, spoiler alert, the electron wave functions in an atom are stationary states, aka standing waves. Okay? They don't change as a function of time. These wave functions, the eigenstates of the electron in the atom, don't change as a function of time. They're stationary states. Okay, now, last thing for today, I'm going to make things, of course, a little bit more complicated. Why not? Since the previous was so easy to understand, why not pile it on a little bit? What is the difference? The difference is that now I'm going to relax this condition that V must be 0. I'm going to say V is not 0. What is it? Well, it's not too complicated. I'm not going to give it a very complicated shape. I'm just going to say it's a constant. All right? So, pretty simple form of the potential energy operator. Just a constant. Before I'm going to show you what that means in terms of the physical interpretation, let me first try to solve this problem. Okay? And you'll see it's very similar to the previous. One small change, but the mathematics follows the same kind of recipe. Okay? So let's write it out first. This is what I'm seeing. Second order derivative all the way to the left. Then the V, which is a constant, times the wave function. And then on the left-hand side, I get the same as before. E, energy, eigenvalue, times the wave function. What can I do to clean this up? Well, on the left-hand side, I get two things. One, an operation, which is a second order derivative. Second, a multiplication. But on the right-hand side, there's also a multiplication. So I just take the multiplication that's there on the left-hand side and move it to the right. Right? So that is going to look like this. Do you agree? I just moved V times psi to the left-hand side. That's all I did. Everything else is the same. You don't believe it?
No.
Oh.
No, I see it.
Then, like we did before, I'm going to take those prefactors on the left-hand side and basically divide them out. So they only appear on the right-hand side. So it looks like this, just like we did before. And then I'm again going to call this whole thing k, k squared, as before. Okay, so it's going to look like this. So the shape of the wave function, or the differential equation, is exactly the same as before. The only thing that changed is the definition of k. What does k look like? It looks like this. The same as before, but now instead of having e, I now have e minus v. That's the only difference. Does that mean that everything else is going to be the same? Well, not really. Why not? Because this is k squared, but k is the square root of this thing. What does that mean? That means that I can run into some very funky scenarios. Because if v has a larger value than e, then this whole thing is going to be negative. Then I have to take the square root of a negative number. The square root of a negative number is a so-called imaginary number. So my k is an imaginary thing. Oh my god. So let's keep that in mind. My general solution is still the same as before. Exactly the same shape, I haven't changed it. But I have changed the definition of k. K can now be something imaginary, depending on the balance between E and V. So let's study that for a sec. All right, that's the function again. That's my definition. It's the same as in the previous slide. Okay, that's the definition. But now I'm going to see what happens. If E minus V is larger than 0, then I basically have the same situation as before. Okay? That means that k squared is larger than 0. That means that the solution is just like this. K is a real number, and the function is basically a wiggly shape. Same thing as before. K just has a different value, but the functional form is the same. What about this? What if V has exactly the same value as E? What if the potential barrier in space has the same energy value as the energy carried by the electron? Then what? Then, of course, it's 0. The difference is 0. That means that k squared is 0. And that is a very odd situation, because if you plug in k 0, that means the wave function is constant. It doesn't wiggle anymore. All right? Now what about this? What if it is less than 0, this difference? V is actually higher than E, meaning the potential barrier is taller than the energy carried by the electron. Right? Then k squared is negative. That's weird. So that means it becomes imaginary. Let's write that out. Here then is k squared. I can write that now in the following way. I'm going to write it. K squared is negative kappa squared, where kappa is just all the constants to them. Kappa squared is defined in this fashion. Okay? So what I'm getting is, if this is negative, then kappa basically becomes imaginary. So if I write now the definition here, okay, this is k squared. This negative sign can be written as I squared, right? Which means I can write k as I times kappa. Sorry, let me hammer one thing down clearly. What I've done here in the definition of kappa squared is, under the condition that V is larger than E, I swap their positions, which means that V minus E is always positive, which means that kappa is a positive number. Okay? Kappa is a positive number. Kappa squared is a real number, but I'm putting here I squared in front of it. So, that means that K equals I kappa. Kappa is a real number, but this I is there. That means if I take the general form of the wave function, I basically do this. Okay? If I plug in this, I get this because there's an I here. This I comes from there, so I get I squared. I get negative kappa x, but kappa is a real number. This is no longer a wiggly function. That is a decaying exponential. What I've done is I basically rewrote k in terms of an imaginary number. And the imaginary number is I times kappa, but kappa is always a positive real number. The total is going to be imaginary because it has to be imaginary since V is larger than E. Okay, just to visualize this, let's say I have a particle that's moving in space and it encounters a barrier. The barrier has value V. Okay, so if my particle now comes from the left, it wiggles in free space, there's no barrier, so it just has an oscillatory shape. Then when it enters the barrier, but my energy that the particle has is higher than the barrier, then it basically goes into the barrier and it just wiggles with E minus V, which is basically meaning that the oscillatory frequency is changing. Still an oscillatory function, but now its frequency is changing. Then when it comes out, it continues as before. Second scenario is, if I come into the barrier, but now the energy carried by the electron is the same energy as the potential energy is high. Meaning that at this point, when the particle enters the barrier, the energy difference is 0, which means it can't wiggle anymore, and it's therefore a straight line. That means the wave function is constant here. Once it comes out, it basically wiggles as before. Now, the last scenario, and of course the most interesting one, comes in, but now the barrier is taller than the energy carried by the electron. In that case, what I'm getting is a shape that is nor constant nor wiggly. In fact, in that particular case, I found a decaying exponential. That basically means that this goes down. The amplitude goes down if it travels through the barrier. Once it comes out, it starts wiggling again, but it wiggles now with a lower amplitude because it has lost that amplitude. This is a very particular scenario that you will not find in classical mechanics, because it means that you can walk through a wall that has a higher energy than you have. It doesn't work. You can certainly go through a wall if you have enough energy, but if you don't, you will not be allowed to go to the other end. Quantum mechanical particles can do that. Okay? So if I erect a barrier in front of an electron, the electron has a certain kinetic energy, potential energy is huge, the electron can still end up on the other side. There is no analog in classical mechanics. This is a purely quantum mechanical phenomenon. All right, folks, that's enough for today.
We out.